In this example, we'll be using the case of a self-driving car. In this case, the car acts as a sort of agent, which is essentially what is learning from your data. The state here on the left describes the current status of the car at any given time. In this case, it could be the car's position on the road, for example. The action here describes all the possible moves that the car can make, such as changing lanes, turning, or simply just maintaining the same speed. And finally, the reward is the feedback the car receives whenever it takes a certain action. The way reinforcement learning works is very simple. You reward good decisions and you penalize bad ones. The more you reward a good action, the more likely the car is to actually do that action. So, for example, if the car decides to signal when it lane changes, that's a good decision. We want to reward that. If you didn't stop at a stop sign, probably not the best idea, and we want to penalize that action heavily. We, of course, do this in a training environment instead of on the real road, where you can run hundreds of thousands of different simulations until the car reaches a sort of idealized state of behavior, where it always makes the good decisions you want it to. Once we have that state, we say that the reinforcement learning agent has converged. What's cool is you can now package up this agent and deploy it wherever you need to, even on edge devices, for example, on the road, and it requires very little computational power. The same principles here apply in a manufacturing environment. So this agent could be a heat exchanger that's trying to save energy, a mixer that's trying to improve the distribution of a fluid within a vat, for example, or even you can imagine a complex chemical manufacturing process that's trying to maximize yield and your product quality.